let's start with getting these different types of numbers out of the way. And the first type of number that I always deal with is the natural number. Now, a natural number is also referred to as a counting number. So for instance, my son, who's 2, he'll start counting and he'll say 1, 2, 3, 4, 5, 7, 8, 10 because, he's 2 and that's just how you learn. Sometimes you miss a few. But anyway, when you first learn how to count, you start using natural numbers. It starts with 1, and then it goes to 2, and 3, and 4, and 5, and eventually you could count forever if you had the time. Those are the natural numbers. Now, the next type of number that teachers usually teach is the whole number. And it's kind of silly that we create a whole new set of numbers for whole numbers because the truth is there's only one difference between natural numbers and whole numbers, and it's the number 0. Everything else is exactly the same. The only difference is the number 0. Now, whole numbers, if I'm thinking about people walking down the street, you could say there's 1 person walking down the street, or 2 people walking down the street, or 3 people, or 0 people. Those are all whole numbers. You probably wouldn't use any other type of number in that situation. I mean, we wouldn't use some of the ones coming up like integers or rational numbers. You can't have -2 people walking down the street. You can't have 2.5 people walking down the street. So we usually stick to whole numbers. Now, natural numbers also count as whole numbers. So if somebody asks you to classify the number 3, you would be able to call it natural and whole. It would technically also be an integer, which is the next type of number we're getting into. And integers are just like whole numbers. It's just now we're allowed to move in both directions. Now we are allowed to talk about positives and negatives. So now -4 here. Before we do that, let's talk about the ... a little bit. This thing, it's technically called an ellipsis, but I don't know if your English teacher has talked about that before. But basically, it's the thing that we use to describe something that goes on forever. Now, with natural numbers and whole numbers, they go on forever in the positive direction. Integers go on forever in the positive direction and in the negative direction. So we have to put that ... right off the bat. And that basically tells us we can go as far negative and as far positive as we want to go. The next type of number we're going to talk about is the rational number. And a rational number is anything that can be written as a fraction. Now, obviously, if you have a fraction like 3/4, that's the one that people get right almost all the time. Hey, it can be written as a fraction, so it's rational. What people don't necessarily understand is something like 0.5. If you're dealing with 0.5 or 0.2 or 1.6, those are all rational numbers. Now, are they written as fractions? No. But could they be written as fractions? That's really the big question. And in this case, yeah, 0.5 is the same as 1/2. And 0.2 is the same as 1/5. And 1.6 is the same as 8/5. So even though they're not fractions, they could be written as fractions, and that's enough to make them rational. Now, the other catch to this whole rational thing, let's say we're talking about, let's say 0.3. And let's put a line over the 0.3. This is the one that students get wrong the most. Because they say, hey, well, this thing's going on forever. And, my teacher always told me that if something goes on forever, then it's not rational. And that's sometimes true. But here's the catch. Could you write a repeating 0.3 as a fraction? Yeah, you could. In fact, it's just 1/3. So you might not have necessarily thought that it was rational, but it is. Just because something goes on forever, that doesn't necessarily keep it from being rational. It's all about, could you write it as a fraction? If the answer to that question is yes, then it's a rational number. In fact, every single repeated decimal in the universe is a rational number. Like 0.36 with a line over it. Okay, 0.36. What the heck is that? Well, I'm not saying you have to memorize it, but I'm going to tell you right now, it's 4/11ths. If you were to get a calculator out and you were to type in 4/11 and see what happens, you would find out that it's a repeating 3/6 over and over and over again. So I guess the question is then, what isn't rational? I mean, that sounds like it covers a lot of things. What wouldn't be irrational? Or what wouldn't be rational? Well, the irrational numbers go on forever, and you have no clue where they're going. So, for instance, if you're dealing with, let's say, 0.7081 ... That would be irrational because it's going on forever, and we don't know where it's going to go next. We have no clue. What's after the ... I don't know. That makes it irrational. So another irrational number we deal with all the time is pi, and you probably dealt with that many times in younger grades or when you're dealing with geometry or whatever it is. Pi comes up a lot, and we know that it's 3.14159265, yada, yada, yada. But we don't know exactly what it is. There are computers that are being run to try and figure out what it is, whatever, but we're not going to get there, so I don't know why we even bother. Also, any radical where you don't have a perfect answer for it, any radical that isn't a perfect square, is irrational. If you were to type in the square root of 11 on a calculator, you would get some crazy decimal that's between 3 and 4. It's going to be closer to the 3. I mean, we can estimate, but that doesn't mean it's rational. An estimate isn't the same as a number being a rational number. You know, radical 11 is going to go on forever. Now, compare that to, say, radical 9. Technically, since that's 3, since radical 9 is 3, we could actually count that as natural. And then because it's natural, that means it's also whole and an integer and rational. And let's just be obnoxious here. Every single last thing that we're talking about, whether we are talking about natural, whole, integer, rational, irrational, everything that we deal with in this section is a real number. Every single last thing. So anyway, let's go to the next section. And this is a really quick section here. It is pretty important to deal with, though. We're talking about the difference between a finite set of numbers and an infinite set of numbers. So let's do the example first. Let's say I ask you to list all of the whole numbers in the universe that are less than 2. I'm hoping that you would get 0 and 1. Those are all of the whole numbers in the universe that are less than 2. But what if I told you to list all of the whole numbers in the universe that are greater than 2? Well, that would be 3, 4, 5, 6, 7, 8. How long would it take you to list them all? Well, pretty much forever. See, a finite set of numbers stops. So finite sets stop. Infinite sets of numbers go on forever. That's the difference. So the first example I gave you, all whole numbers less than 2, that is a finite set of numbers. The second list I gave you is an infinite set of numbers. So basically anything that would take you forever. So if you have a teacher that tells you, hey, your homework for tonight is to list all the whole numbers greater than 2, I'm pretty sure you're not going to get it done. I'm pretty sure maybe your teacher just didn't really like you very much and wanted to keep you busy for a while. I don't know, something like that. Anyway, let's go on to the last part of this lesson. That would be the number properties. And let's start with Well, we usually start with the letter A, so let's do that. Let's start with the associative property. And the associative property is basically who you associate with, who you group yourself with. And when it comes to addition and multiplication, it doesn't matter. So let's say I gave you 2 plus, and then the 3 and the 4 are hanging out. That's exactly the same as if the 2 and the 3 are hanging out, and then the 4 stays to the side. So it doesn't matter at all how they associate. The answer is still exactly the same. Makes no difference. I mean, the left side is 9, the right side is 9. Not too hard to figure out. Now, when it comes to multiplication, the rule is exactly the same. Obviously, we're going to use multiplication symbols instead, but it's still the same concept. So hang on just 1 second. There you go. And as you can see, in the first example, the 3 and the 4 were being grouped together. And in the second example, the 2 and the 3 are being grouped together. But if you actually crunch the numbers, if you actually try and figure out what the answer to both sides are, well, it's the same. 24 on the left, 24 on the right. That's a number property. It holds true every time for addition and for multiplication. It does not hold true for subtraction and division. That's why we don't talk about it for subtraction and division. All right, next up, now we're going to talk about the commutative property. And, this property just says you're allowed to move the numbers around however you want. 5 plus 7 equals 7 plus 5. Okay, I think you already knew that. Maybe you just didn't know what it was called. Same thing with multiplication. 5 times 7 equals 7 times 5. So it's the same for addition and multiplication. Once again, if you tried to put division symbols in instead of multiplication symbols, this property would not be true. Let's get through this real quick. Let's go with the identity property. Your identity is who you are. So let's say you've got the number 3 and you don't want it to change. It likes being who it is. Well, add 0 to it and it wouldn't change. 3 plus 0 is still 3. Now, when it comes to multiplication, if you don't want the number to change, don't use a 0, use a 1. Okay? If you are wanting to cancel out a number, that's when you would use the inverse property. That's when you're trying to take the number and go into reverse here. So in this case, let's say we have this 3 and we want to get rid of it. We want to bring it back to 0. Well, you could add a negative 3 to it. Now, when it comes to multiplication, it comes out a little bit differently. Let's say you've got the number 5 and you want to cancel it out. I'm going to write this one in by hand here. What would you multiply it by? Well, you would multiply it by 1/5. The 5's cancel out. Now, in this case, you're not going to get a 0 at the end. You're going to get 1 at the end. All right. 2 more properties here. The distributive property, I think you know that one. That's if you have a 3 and then let's say 2x plus 5 on the inside. It comes out to 6x plus 15. You just multiply them. No big deal. And then the last one, the closure property. That means if you've got 2 real numbers, you add them together or you multiply them, yeah, you still get a real number. So let's say you've got 2 times 3. Well, 2's real, 3's real. Hey, guess what? 2 times 3 is real too. So that works for addition and multiplication. Not necessarily division. Anyway, thanks for tuning in, guys. I appreciate that. Hope this helped out with your lesson, and I hope to see you guys some other time.